h is less than or equal to 0, it is a C1 function. It's strictly convex. Even. And I keep saying even is not important. And the limit when s goes to infinity, h of x over s to the power p is infinity for some p between 1 and infinity. And I define the cos c of x, y. The cost for transporting a unit mass from s to y is h of x minus y. I am giving mu naught, mu1, Borel probability measure on RD.
You want that this h vanish at 0, or it's not necessary?
No, it is not necessary. And mu naught, mu1 absolutely continue with respect to Lebesgue measure. The support of mu naught and the support of mu1 are in the ball center at the origin of radius r. And j of uv equal to the integral over rd of u d mu naught plus the integral over rd of v d mu 1. And I am going to consider j on uc. This is the set of uv such that uv is from rd to negative infinity plus infinity, is upper semi-continuous. U is not identically negative infinity. V is not identically negative infinity. And u of x plus v of y is less than c of xy for every x, y in Rd. So I'll also have gamma, mu naught, mu1. This is the set of gamma, Borel probability measure on Rd cross Rd, such that the first marginal of gamma is mu naught, and the second marginal of gamma is mu1. And again, what this means is if you integrate over Rd a function depending only on x, you get the integral over Rd cross Rd of f gamma ds dy. And the same thing, if you integrate a function depending only on y, you get the integral of gamma dx dy. So let me do the following convenient identification. The measure I have mu naught of Rd minus the closed ball of radius r is 0. So this implies that if I integrate u on Rd minus the closed ball of radius r, I get 0. And so it doesn't matter what the value of u is outside the closed ball. Therefore, we identify u from the closed ball to negative infinity, with the function u bar from Rd to negative infinity, defined by u bar of x is u of x if x is in the closed ball, and equal to negative infinity if x is not in the closed ball. Here is a summary of what we proven. If there exists u naught, v naught in UC such that j of u naught, v naught is bigger than or equal to j of uv for every uv in UC, if we had that property, and if we know that and u naught is v naught c, where v naught restricted to the complement of the ball is negative infinity. If we have this property, then this implies existence of a minimizer in Monge problem. So that is the first conclusion. This is what we prove. And we also prove that, let me call the minimizer T naught in Monge problem. We also prove that J, in that case J of U naught V naught, is the Monge cos at T naught. So let me recall what is that. This is the integral over Rd, C of x, T naught of x, mu naught dx. And so we have the duality result we want. And u naught of x plus u v naught of t naught of x equal to c x t naught of x if the gradient u naught of x exists. Okay. So what I plan to do now is to prove this statement. And so, as a consequence, we'll have what is below here. Yes?
Could you tell something about the idea that people are going to insist nowadays to look like T naught, like a coupling? I mean, or in fact,
Why is it interesting to look
at this T naught or pi 1, pi 2, like handle variables, like so if you insist on this, because in this context, you're coupling the measure V naught and V1.
Yes.
If this is given by capital T, this is a deterministic coupling.
Yes. So the relation with coupling is instead of that, what I wrote here, I can write the integral of C of a random variable, x of w, y of w, dw, the infimum of this, subject to the condition that the random variable x has mu naught as a law, and the random variable y has mu1 as a law. I can do that. But if I can show that y is invertible, x is invertible, then I can write this as the integral of C of x, y composition S inverse of x mu naught dx. And y composition S inverse will be my T naught. So what is hidden behind that is, in fact, if I look at the problem as coupling two random variables, I have invertibility of x and of y. Right? So here I use the inverse of x, but I could have used the inverse of y too. Okay, so let us prove this theorem. There exists U naught, V naught from BR into R, Lipschitz, such that U naught of x plus V naught of y is less than or equal to C of xy for every x, y in the closed ball. U naught equal to V naught C. So what I am doing here, I said to define the C transform of a function, the function has to be defined on RD. And what I said here is whenever I define a function on a ball, on the ball, I identify it with its extension to RD by this formula. So in other words, what I am writing here is U naught of x is the infimum y in the closed ball, C of xy minus V naught of y. So note that when I take the extension, when we are not on the ball, when U naught is negative infinity, V naught is negative infinity, V sum is negative infinity, and so the inequality holds. So we are still in U bar C with the extension. Because my function are Lipschitz, I have immediately the property that they are not identically negative infinity, and they are continuous, or they are upper semi-continuous. So we have that property, and J of U naught, V naught, is bigger than or equal to J of UV for every UV in UC. So proof. So let me start by avoiding triviality. 0, 0 is in UC. And so J of 0, 0 is smaller than the sup over UC of J. Okay, so the sup is not a negative infinity. This is less than. We did the computation. Let me repeat it again. U of x plus V of y is less than C of xy. Take gamma to be mu naught, mu 1. Then if I integrate, I have U of x d gamma plus the integral of V d gamma is less than the integral of C xy d gamma. So that is the integral over Rd mu 1 dy. I am using Fubini. The integral over Rd C xy mu naught dx. Now, mu naught is 0 outside the ball of radius r, and mu 1 is 0 outside the ball of radius r. When s and y are in the ball of radius r, c is less than the supremum of h on the ball of radius 2r. So I am using the fact that mu 1 and mu naught are probability measure, and so if I integrate a constant, I get 1. So this is less than the supremum on the ball of radius 2r of h. And so the supremum is not plus infinity. Let un, vn, be in C, be in UC, be such that the limit when n goes to infinity of J of un, Vn, is the sup of J over UC. Okay. So I have a supremum, and I can characterize that by a maximizing sequence. This un and Vn, they are just upper semi-continuous. They are just upper semi-continuous. And I don't know any better property of that. So if I want to extract a subsequence, I don't know that the un and Vn has some good convergence property. I don't know, for instance, that they converge uniformly. And if I knew that they converge uniformly, then I will have a limit of a subsequence, u, v, and that will be certainly a maximizer. So I am going to modify u, n, and vn. So let us remember that we show this property. The fact that uv is in, if you take uv in uc, it satisfies this property. And so this holds for every y. Therefore, u of s is less than the infimum over y, and this is vc of x. So the fact that uv is in uc, this implies that u is less than vc. But clearly, by definition, vc of x is the infimum over y of c of xy minus v of y. This implies that vc of x is less than c of xy minus v of y for every y, which implies that vc and v belong to uc. So I start with a uv. I replace it by vc, v, which is still in uc, and vc has a larger value than u. So I can conclude that j of uv is less than j of vc, v. So since uc, un is less than vnc, and vnc, vn is in uc, we have that the limit when n goes to plus infinity, j of vnc, vn, is the supremum of j. So now I have improved my sequence because now I have something here which is Lipschitz. I am going to repeat the procedure. Repeating. The argument. We have. So this argument says that when I have un and v bar n, I can replace one of them. I can repeat the argument here and say that the limit when n go to plus infinity, j of v bar nc, v bar n cc is the supremum of j. So the way I do that, I give a new name to this. I call it an, bn, and I repeat the argument I have here, and I am going to replace g of an, bn by g of an, anc. And g of an, anc is what I wrote there. So now I see that here I have a Lipschitz function, and then there I have a Lipschitz function. So I started with a sequence which may not have a good property, and I replace it by a maximizing sequence which has a better property. So observe that the Lipschitz constant of, let me say set un to be V bar n, Vn. Sorry, it is n here, and it is C. Set Un to be Vnc, and Vn to be Vncc. Observe that the Lipschitz constant of Vn and the Lipschitz constant of Un is less than R. And one of the things we prove is we prove that if you take A, C, 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 you get AC. So in general, you have A, C, C is bigger than or equal to A. And we prove that when you add one more C, you have equality. This is like what happened with the Legendre transform of function. If you take a function, you compute the Legendre transform twice, you take a function f, you compute the Legendre transform twice, you call it f star star. F star star is less than or equal to f. If you compute it a further time, f star 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 equal to f star. So this is the analog of what you have for the Legendre transform with a reverse inequality. So if I compute UNC, this is Vn bar Cc. And so this is Vn. If I compute Vnc, this is V bar. This is V bar N C C C, which is V bar N C. But V bar N C is UN. And so what I remember is this equal to that, and that equal to this. Yes?
Didn't we show that those Lipschitz constants of Vn and Un were less than some soup of the gradient of h on the big ball, right? Of radius r plus little r?
Yes.
Because you wrote like less than r instead.
Less than 2r. So we wrote that if you look at the restriction of Un to the ball of radius r, the Lipschitz constant is less than r plus r.
Isn't that the soup of the gradient of h on this ball of radius r plus?
Oh, yes. Yes, thank you. It is less than the soup of a gradient of h over the ball. Yes, this is what it is. Yes, thanks. Yes. So call that M. Okay. So we have the Lipschitz constant of my function are uniformly bounded. Now, take the function un equal to n, the constant n. The Lipschitz constant is 0, but I don't have a convergence of any subsequence, uniform convergence on its subsequence. So to apply the Ascoli-Arzela, which will tell me that I have a uniform convergence, I need to know that un of 0, for instance, is bounded independently of n. So here is the observation. Call this one observe that j of u plus lambda, v minus lambda, is the integral over Rd of u plus lambda d mu naught plus the integral over Rd of v minus lambda d mu 1, which is j of uv plus lambda mu naught of Rd minus lambda mu 1 of Rd. And so this is j of uv, because mu naught of Rd equal to mu 1 of Rd. And so if I add a constant to u and subtract a constant from v, I don't change the value of j. In particular, replacing Vn by Vn minus Vn of 0 and Un by Un plus Vn of 0, we may assume that Vn of 0 is 0. Okay? So if Vn of 0 was not 0, I add a constant to it, and I get a new function. And this is not going to affect the property 1. So call this 2. By 1 and 2, I have that Vn of x is Vn of x minus Vn of 0. And so in absolute value, it is less than the Lipschitz constant of Vn multiplied by x, r. So for x in the ball of center 0 radius r, I have this, which is less than mr. And so Vn is uniformly controlled. Hence, by the Ascoli-Arzela theorem, a subsequence of Vn, we still label Vn converges uniformly to some V, which is from the Coles ball to R. But if I compute un of 0 or un of x, this is Vn. This is Vnc of x, and so it is the infimum over y in the closed ball c of x y minus Vn of y. So I have a c of xy minus Vn of y is bigger than, c is bigger than 0. Vn is bigger than by that. Vn is bigger than negative mr. When s and y are in the ball of radius r, C of xy is bigger than the maximum of h on the ball of radius 2r. So I have replaced this by h of x minus y. And if s and y are in the ball of radius r, s minus y is in the ball of radius 2r. And negative Vn is less than mr. So I can conclude, and so un is less than mr plus the supremum over the ball of radius 2r of h. As before, as done with Vn, we may assume that un converges uniformly to some u defined from the closed ball into R. Clearly, un of x plus Vn of y is less than C of xy for every xy in the closed ball implies u of x plus v of y is less than C of xy for every xy in the ball. So passing to the limit, I have uniform convergence, therefore I have pointwise convergence. And so uv is in C. Is in UC. We have J of UV equal to. So let me, my theorem says there exists U naught V naught. So let me change the notation here and say this converges to some V naught, and that converges to U naught, and we have this. If I look the expression of J of UV is the integral of U d mu naught plus the integral of V d mu 1. Here I have a probability measure. Therefore, this functional is continuous with respect to uniform convergence. That functional is continuous with respect to uniform convergence. So I can write that this is the limit when n goes to plus infinity, J of un Vn. But that is, by definition, the sup of J over UC. And I have a maximizer. Can I conclude that U naught C is V naught and V naught C is U naught?
You can change, right? Because you already proved that if you change by the C transform, you grade.
Yes. Yes. So if this was not true, but that is true, if this is not true, I can replace this by, I would say that U naught C I will say that V, not C. V is a maximizer, and I will repeat the procedure to have that property. However, for each x in BR bar, there exists y n in BR bar such that un of x equal to c of x yn minus vn of yn. So I am saying that the fact that un is vnc, this implies that for each n I have that equality. Now take a yn is in the closed ball of radius r, therefore it has a subsequence which is convergent. The subsequence will converge to a certain y which remain in the ball. This function, you converge it uniformly. So I have, this goes to u naught of x, that goes to c of x, y, and this will go to v naught of y, which imply that uc, vc, u equal to vc. Because it implies that not only I have this inequality, but for each x, I can find a y such that equality holds. So it is easy to check that u naught c is v naught and v naught c is u naught. And that concludes the proof of that theorem. Any question?
As the y for which you have that e, is that?
Yes, so for each s, the unique y for which I have, the unique y which minimizes will be t of x.
And this t is the solution of the moment problem.
Yes.
Have you used the distributed convexity?
For gradient of h to be invertible, because gradient of uc x is gradient of h x minus y, when the minimizer is at 10 at y. And if h is invertible, then y is uniquely determined.
So I don't know what is your plan, but if you could make somehow an overview of all the, at least of this theorem, because it is connect many different things, right? You have the Kantorovich problem, and you have the Monge problem, and now you prove that this T is connected with the C, how to say, C transformer.
Yes.
Conjugate, right?
Yes.
So there is several different ideas to playing. I don't know, but since we are more or less closing this, how to say, this section.
Yes. So let me summarize. So if you take UC to be the set of UV such that U lower upper semi-continuous, upper semi-continuous, etc., and this inequality holds, then the graph of this functional is below the graph of that functional and the graph of that functional. So here I am taking gamma, which has mu naught and mu 1 as marginals, and I am taking T, which possesses mu naught for mu 1. So this is a 10-minute proof, very, very easy. Whether mu naught and mu 1 are absolutely continuous with respect to Lebesgue measure, whether the support is bounded, this inequality is easy to establish. Call this one. So what we've done is we find a maximizer of this, and we call it U naught V naught. And we don't know if U naught V naught has some good smoothness property. But we made the following observation. This function is linear. This set is convex. So if I am looking for a maximizer, I can look for a maximizer among the extreme points. Now, the extreme points will satisfy the property that the inequality here cannot be straight. Because if the inequality was straight, I can increase the value of U and not violate the inequality, and this will increase the value of that integral, and I cannot have a maximizer. So saying that the equality is not straight, that you have equality for each x, is equivalent to saying that you can write a U of s is the infimum over y of C of xy minus V of y. So given V, the largest function U for which this inequality holds is U given by that. Any over U will be smaller than or equal to that. So the extreme point satisfies some regularity property in the sense that they are locally Lipschitz. But when I am doing this, if I minimize over RD, I will not have that this is Lipschitz. So I needed to impose that the support of mu naught is compact, the support of mu 1 is compact, and so I can write the infimum over the support of mu 1, and this gives me immediately that my functional is Lipschitz. Because the gradient of U is the gradient of H at x minus y. So if I take S in a bounded set and Y in a bounded set, it gives me immediately that the gradient of U is bounded. So step 1, we have looked at the case mu naught, mu 1, absolutely continue with respect to Lebesgue measure, and the support of mu naught, the support of mu 1 are compact. And in that case, we prove equality in 1. Now, we want to remove this condition and remove that condition. Step 2, mu naught, mu 1, arbitrary. And I want to still show that the equality hold. So this is the idea. You write mu naught as a limit of mu naught n, where the support of mu naught n is in the ball of center 0 radius n. So this limit is the weak star limit. I am going to write mu 1 to be the limit, mu 1n, the weak star limit, the support of mu 1n is in the ball of radius n. And I am going to set gamma n to be gamma Tn. So between mu naught n and mu 1n, I have an optimal map Tn by the first step. And since we said that the cost function of Kantorovich and Monge, these two cost functions, they coincide when gamma is given by a map. Okay. So one is tempted, actually it is true, one is tempted to try to show directly that if I let n go to infinity, gamma n will converge to gamma, which is the minimizer corresponding to mu naught and mu 1. That is true. But if you try to make a direct proof, there are some heavy concept of measure theory of probability you need to know. And I don't want to go that route. So here is the difficulty. I have the cos of Monge is bigger than or equal to the cos gamma Tn when gamma is in mu naught n, mu 1n. Now I am taking gamma bar in gamma mu naught mu 1. When I take gamma here, it is not there. So I cannot use the information here to compare. I cannot use the information here to compare the cost of gamma bar to the cost of this limit. if I want to do that, I need do something from measure theory telling me that when I have my gamma here, I can modify it to have another gamma bar, which is close to this one, and which satisfies that property. So again, I am minimizing on two different sets, this set and that set. And I cannot compare the element of this set to that set. But there are some concepts from probability which will help me approximate what is here by something there. And I can compare the two minimization problems. I don't want to go that way because this will take too much energy. So here is some beautiful fact. This is a geometric characterization. It says the following. Take gamma in that set. I want a geometric condition, necessary and sufficient condition for gamma to be optimal. The condition is the support of gamma C cyclically. I will say what this is. Monotone is equivalent to gamma optimal. So there is a geometric characterization of the support of any given measure to be optimal. So what does a C cyclically monotone mean? Assume that I decide to send S1 to Y1, S2 to Y2, and I compute the cost. The cost will be CS1, Y1, plus CS2, Y2, with a 1/2 in front of it. But let me ignore the 1/2. That strategy must be necessarily better than sending S1 to Y2 and S2 to Y1. So if my gamma will be optimal, that is a necessary condition it must satisfy. If I take S1, Y1 in the support of gamma, S2, Y2 in the support of gamma, if I change the order, I should increase the cost. This is a necessary condition. It is not sufficient. The necessary and sufficient condition is the following. If I take an arbitrary number, y1, s1, y1, sn, yn, in the support of gamma, and I look at the cost sum csi, yi, I from 1 to n, 1 over n, and I compare it to the cost csi y sigma I. So if I decide to permute the point yi or the point si, then I get a cost which is bigger than the original cost. This must be satisfied for every n, and that is a necessary and sufficient condition for gamma to be optimal. So here is the idea. Gamma Tn is a C cyclically monotone. When you pass to the limit, gamma infinity, the limit of gamma Tn is a C cyclically monotone. And so the limit is optimal. Right? So what one is going to do for the limit is if I take a S1, Y1, Sn, Yn, n is not a good, let me call it K. To S, K, Yk, then each S1 is the limit of S1n, Y1n. And so when I put Sin, Yin, I have this inequality. When I let n go to infinity, this inequality will hold for the limit. And so it is easy to prove that the support of the limit of gamma Tn is cyclically monotone. So in the first homework, I think it is exercise 1.3. The exercise asks to prove that assume you have a sequence of measures converging to a measure. Anytime you take a point in the limiting measure, it is the limit of a sequence of points in the sequence of measure. So what I am saying is if z belongs to the limit of gamma Tn, then z is the limit of Zn, where Zn belongs to the support of gamma Tn. So if Z belongs to the support of the limit, then Z is a limit of element of the support. And so once you have that property, it shows that if gamma Tn is optimal, then the limit of gamma Tn will be optimal.
Just wondering, this gamma, so the only thing about gamma that is entering this characterization that you gave there is the support. So where the mass of gamma comes into play in this inequality, for instance. So you put the equal mass for all this C, Hy, Xi, Hy, just the arithmetic mean.
Yes. Okay. So you are asking what does this has to do with?
Yeah, because there is this mu0, mu1, and then you form a gamma, and this gamma mu0, mu1, but after all, you just consider this arithmetic mean.
Yes. So here is my statement. I forget about mu0 and mu1. You give me gamma, a measure on Rd cross Rd. Assume that it is cyclically monotone in the sense that this inequality is satisfied whenever I pick point in the support of gamma. Then I claim that if I take mu0 by definition to be the first marginal of gamma, mu1 by definition to be the second marginal, then gamma is the optimal measure which is going to couple mu0 to mu1. So this is a geometric characterization. I am characterizing the possible set. When you give me any gamma, I have a geometric characterization of the gamma such that they couple the marginals in the best way.
Still have a doubt. So where gamma is coming into play in this, for instance, in this inequality, what you are requiring from gamma? Just see there is some connection of C with gamma? No.
But C is entering here.
Okay, C is there, right. C is a function, two variables, and maybe it's an h of x minus y, I don't know, right? But so this gamma, you are only using that this xi, yi, they are in the support of gamma. You are not using anything about the mass of gamma. For gamma could be distributed anyway, and then you would just take this arithmetic mean. So this is my doubt. I'm not seeing.
For every k and every si,
there is nothing about the mass of gamma. So you just need to take the arithmetic mean, and then you characterize that way. So the gamma satisfies this inequality. Well, gamma, but there is nothing about gamma, right? Just C. So
But
C
the SI, YI are taking the support of gamma.
so the only thing you are using about gamma is the support of gamma. This is the thing that's puzzling.
Okay, so let me give you an example. Pick up any convex function. Right? And we know how to characterize convex function. Right? Convex function is the second, say a smooth function. It is convex if and only if the second version is non-negative. So you pick any convex function. Let's say smooth to make things easier. And you pick a measure, mu0. And you define a mu1 to be the push forward of mu0 by the gradient of phi. So let C be a function of class C2. Let mu0 be a probability measure on add. Assume, for instance, the second moment is bounded. Define mu1 to be the push forward of mu0 by the gradient of C. If phi is convex, then the integral of x minus gradient psi of x square mu0 dx is less than the integral of s minus t of x square mu0 dx for all t such that t push forward mu0 to mu1. Okay, so that is an example of what I wrote there. So I am saying I give you give me a psi, which is a convex function. And now you pick up a mu0 any way you want. But once you pick up mu0, I have no choice. I have to define mu1 to be the push forward of mu0 by the gradient of psi. When I make this definition, I have found the optimal map between mu0 and mu1. So a generalization of that is you give me any measure gamma which satisfies this geometric property. And then you look at the first and second marginal of gamma. I claim that if you take any other gamma tilde, which has this first and second marginal, then the original gamma has the smallest cos. Any question?
It is still surprising result, don't you? But I agree with Professor Herman that it's strange that you don't consider the mass on the points. You don't consider just as you consider just the support of gamma, and you obtain such a result. It's surprising.
Yes, it is a surprising result. So this is this may be due to Knock and Smith. Yes, and this is a remarkable result, that you have a geometric characterization of the optimizer. Okay, so still, this is not the most important step. To make an analogy with the next step, let me recall a result of, it may be due to Rockefeller, but it may be older than Rockefeller. Take a set S to be a set of RD cross RD. And you take C of X is the norm of X minus Y squared. So saying that S is C cyclically monotone is equivalent to saying that for every k integer, every S1, Y1, Sk, Yk in S, for every sigma from 1k to 1k permutation, bijection. Okay. So saying that S is C cyclically monotone is equivalent, is that. This is the definition. But usually in the literature, the definition appears in a different way. So note that it is not a loss of generality to take this permutation, which is going to send I to I plus 1, because I just change the order of the point, and I can always assume that I am in such a situation. With the convention that when I choose this, I am going to say that Sk plus 1 is by definition S1. And Yk plus 1 is by definition Y1. Okay. Now, the left-hand side is the sum Si squared plus the sum Yi squared minus twice the sum Si Yi. The right-hand side is the sum Si squared plus the sum Y sigma I squared minus twice the sum Si y sigma I. So can I simplify this? What can I take out? Okay, I take this out. Can I take more out? Okay, this equal to that because sigma is a permutation. And what you will find often is 0 is less than the sum of yi minus y sigma I Si. Right? So this is the definition used by Rockefeller, which is equivalent to what I wrote above. So here's his theorem. S cyclically monotone. So when C is S minus Y squared, he called it cyclically monotone, if and only if there exists phi convex, such that S is in the subdifferential of phi. Okay. So I need to add a phi convex lower semi-continuous, such that this condition is satisfied. But this is equivalent to psi equal to psi star, star, star. A function is convex if and only if it is twice its Legendre transform. Therefore, S is cyclically monotone if and only if S is in the subdifferential of a phi, a psi, such that psi equal to psi star star. A consequence of that is if you write phi of x plus phi star of y, you get that this is sy if x, y is in the subdifferential. And so if sy is in S, since it is in the subdifferential, phi of S plus phi star of y is x inner product y. So this reminds you the equality which appear in the duality u of x plus v of y equal to, for every x, there exists y such that u of s plus v of y is a c of xy. So what the plan will be, it is very easy to prove that S is C, cyclically monotone, if and only if S is a subset of the C superdifferential of a function. And we will have u of x plus v of y equal to c of xy if xy belong to S. So if I take S to be the support of gamma, I have this equality on the support of gamma. And so this tells me that I have the duality I need, because when I integrate the left-hand side with respect to gamma, I have j of uv. When I integrate the right-hand side, I have the integral of c d gamma, which is the Mont cost. So I will have that j of uv equal to the integral of c d gamma, which is the duality we have been trying to prove. Any question? So let me solve an exercise. So this exercise will say that that approximation is possible and it has some good property. So this is part of the homework number 1, but I am going to explain why this is true. Let mu be a Borel probability measure. On RD. Show that there exists a sequence mu n absolutely continue with respect to Lebesgue measure, probability measure, such that the support of mu n is a subset of the closed ball of radius n, and the limit when n goes to plus infinity, the integral over Rd of phi d mu n is the integral over Rd of phi d mu for every phi which is bounded on Rd and which is uniformly continuous. So in particular, if I take a phi continuous of compact support, then this equality holds. So I am saying that I can draw a conclusion which is stronger than have a weak star limit. Weak star limit will take a phi to be continuous and of compact support, but I am allowed myself to take a function which may not be of compact support and which are uniformly continuous. You can write an explicit representation of un the following way. So take a standard mollifying function. So take rho of class C infinity of compact support in Rd. Rho is greater than or equal to 0. The support of rho is the ball of center 0, radius 1. And rho is even. And the integral over Rd of rho is 1. So set rho epsilon of x to be 1 divided by epsilon to the power d, rho of x over epsilon. So this is a standard mollifier. And define g bar epsilon of x. This is the convolution T1 over n. This is the convolution of mu of rho 1 over n with mu. So check that. If you integrate over Rd phi gn, g1 over n ds, this is the integral over Rd of rho 1 over n convolution phi d mu. But because phi is uniformly continuous, this will converge uniformly to phi. However, I don't yet have the condition that the support of the measure is compact. So define mu n to be g 1 over n, the characteristic function of the ball of this ball. By the Lebesgue measure. Okay. So now I have a measure which is absolutely continuous with respect to Lebesgue measure, which is of compact support. But I lose the property that I have a probability measure. So I'll have to divide by lambda n, where lambda n is the integral of over the ball of g1 over n ds. And this does the job. So the next exercise will say that if gamma n has mu naught n and mu 1 as a marginals, then the limit gamma has mu naught and mu 1 as a marginals. This is a little bit stronger than saying that the set gamma mu naught, mu 1 is compact. Saying that the set is compact is if I take any sequence, I can extract a subsequence, which is convergence in that set. But now I am taking a sequence. I am letting the set vary. And I want to prove that I can take a subsequence such that the limit is in gamma mu naught mu 1. Let mu naught n, mu 1 n, be Borel probability measure such that the limit when n goes to infinity, the integral over Rd of phi d mu naught n equal to the integral over Rd of phi d mu naught, the limit when n goes to infinity, the integral over Rd of phi d mu 1n is the integral over Rd of phi d mu 1. And this holds for every phi which is continuous, Rd, and uniformly continuous, bounded and uniformly continuous. Show that if gamma n has mu naught n, mu 1 n as marginals, and gamma n converges with star to gamma, then gamma has mu naught and mu 1 as marginals. And again, in all these things, one is going to worry about what happens when the mass goes to infinity. Because with star convergence is you multiply by a test function, which is of compact support. Typical example, take delta n. Take my measure to be delta n. You let n go to infinity, the mass escape to infinity, and the limit of my measure is 0. So I don't have preservation of mass. But this condition the fact that I am taking the test function, I don't impose that they are of compact support. This is going to help me saying that mass does not escape to infinity, and I will still have a probability measure. Solution. The idea is always a cutoff function. I am going to take r plus 1, negative r minus 1. And I am going to take the function which is 1 on negative r, which is linear. So call this phi r, so that 0 is less than phi r is less than 1. The Lipschitz constant of phi r is 1. And the limit of phi r the support of phi r is the set negative r minus 1, r plus 1. Let f be a function of compact support in Rd. We have to show that the limit, when n, we have to show that the integral over Rd of f d mu naught is the integral over Rd cross Rd f of x gamma ds dy, and call this 1, and the integral over Rd of f d mu 1 is the integral over Rd cross Rd of f of y gamma dx dy. So I am only going to show 1, and the proof of 2 will be similar. The integral over Rd, okay. So observe that gamma of Rd cross Rd is less than or equal to 1. Okay. Because of the total variation is a lower semi-continuous function. Now, you write the integral over Rd cross Rd of f of x gamma n ds dy. This function is not of compact support in the y variable. So I am going to correct that and write that this is the integral over Rd cross Rd of f of x phi r of the norm of y, gamma dx dy, gamma n, plus the integral over Rd cross Rd of f of x, 1 minus phi r of the norm of y, gamma n dx dy. Similarly, the integral over Rd cross Rd of f of x gamma dx dy equal to with gamma. But this is the integral over Rd of f of x mu not n f d mu naught n. So I am using the fact that gamma n has mu naught n and mu 1 n as marginals. So I subtract s, the absolute value, the integral over Rd of f d mu naught n, minus the integral over Rd cross Rd of f of x gamma dx dy is less than or equal to the integral over Rd cross Rd of f of x psi r of y d gamma n minus gamma dx dy plus the integral over Rd cross Rd. I will take the L infinity norm of f, and I will take 1 minus phi r y gamma n dx dy plus the L infinity norm of f, the integral over Rd cross Rd of 1 minus phi r of y gamma dx dy. Now here we have a function of compact support in both variables. This will go to 0. So thus, when I pass to the limit here, because I have this property, I can conclude that the integral over Rd of f d mu naught minus the integral over Rd cross Rd of f of x gamma dx dy is less than. This will go to 0. I'll have the L infinity norm of f. Now, I am going to use that this is the integral over Rd, 1 minus phi r of y, mu 1n dy. The second marginal of gamma is mu 1n. The functional I am integrating depends only on y, and so I can replace that integral by integral with respect to mu 1n. Again, I am in a situation, this function is Lipschitz. 1 minus that function is then uniformly continuous. When I had uniform continuity, this limit goes to that. And so this is going to disappear from my expression. I will be left with the integral over Rd cross Rd of 1 minus phi r y gamma dx dy. This measure, gamma, is finite. I have a function here which is between 0 and 1, and it is less than 1. The Lebesgue-dominated convergence theorem tells me that I can pass the limit r going to infinity from outside to inside. When I pass it from outside to inside, this goes to 0. So that goes to 0, which concludes the proof. Any question? Yes, so I'm going to stop.